So this is the basic initial feasible solution that we had obtained in the previous step. Now, in order to test whether this initial feasible solution is optimal or not, we have to first find out if this solution is acceptable to proceed with optimality test. So basically the next step is to test for acceptability of this solution. So for the acceptability test, there are two conditions. The first condition is that the number of allocations should be equal to m plus n minus 1. M is the number of rows, n is the number of columns. So in our case, m is 4 and n is 5. There are 5 columns, 1, 2, 3, 4, 5, and minus 1. So this is equal to 4 plus 5 is 9, minus 1 is 8. Now let's calculate the number of allocations that we have. So 1, 2, 3, 4, 5, 6, 7, and 8. So number of allocations is equal to m plus n minus 1. So this condition is met. Now the second condition is that the allocations should be in independent positions. So what this means is that it is not possible to change any individual allocation without either rearranging the positions of the allocations or violating the capacity and demand constraints. Now, a simple rule of thumb for allocations to be in independent position is that it is impossible to travel from any allocation back to itself by a series of horizontal and vertical jumps from one allocated cell to another allocated cell without a direct reversal of the route. So let's take for example this cell, which is FAS3. Let's try to create a closed loop with the help of horizontal and vertical lines jumping from one occupied cell to another and trying to reach back to this cell here. So if I start from here and then move here to FAS2 and then to FCS2, from here I can't move to any occupied cell with the help of horizontal or vertical lines. So this will not work. So let's try another one. So from here, let me go to FBS3 and then to FBSD. Again, from here I can't move to any allocated cell using horizontal or vertical lines. So basically what this is proving is that there is no way I can create a closed path for this allocated cell by jumping to other allocated cells using horizontal and vertical lines. So that means that this is in independent position. So similarly, if you evaluate all the other squares which have allocations in it, you'll realize that all of them are in independent positions. So both these conditions are met. So what this means is that we can now proceed with the optimality test. Now there are two methods for performing the optimality test. For this example, let's use the modified distribution method or the UV method. Now the first step in the optimality test using the modified distribution method is to set up a cost matrix containing the unit costs associated with the cells for which allocations have been made. So basically we have to create a matrix with the unit cost of the cells where there is an allocation. So let's do that. So this is the matrix that I've created. On the left hand side I've placed the factories, and these are the stores S1, S2, S3, S4. Now let me place the unit cost of the cells where we have an allocation. So 4, 6, 8, 10. There's one more I missed. SD 0, 4, 13, and 8. Now the next step is to assign the variable ui to each of the rows and vj to each of the columns. So let's say this is u1, u2, u3, u4, and v1, v2, v3, v4, and v5. The next step is to compute the values of u and v for the stone squares, that is the squares where we have an allocation, such that ui plus vj is equal to cij. Cij is the cost associated with that row and that column. So for the first square, u1 plus v1 is 4. For the second square, u1 plus v2 is 6. For the third square, u1 plus v3 is 8. For the fourth one, u2 plus v3 is 10. For the fifth, u2 plus v5 is 0. Sixth, u3 plus v2 is 4. For the seventh, u4 plus v3 is 13. And the last one, u4 plus v4 is 8. Now since we have taken 4 plus 5, which is 9 variables, but the number of allocations is equal to 8, we'll assume one of the variables as 0. So let's assume v1 equals to 0. And with that assumption, let's try to find out the values of all the variables. So v1 is 0, so u1 becomes 4. Now u1 is 4, so v2 is 6 minus 4, which is 2. Now u1 is 4, so v3 becomes 8 minus 4, which is 4. Now v3 is 4, so u2 is 10 minus 4, which is 6. Now u2 is 6, so v5 becomes 0 minus 6, which is minus 6. Now v2 is 2, so u3 is 4 minus 2, which is 2. So u3 is 2, v2 is 2. Now we know that v3 is 4, so u4 becomes 13 minus 4, which is 9. So u4 is 9, v3 is 4. Now v4 is 9, so u4 becomes 8 minus 9, which is minus 1. So u4 is 9 and v4 is minus 1. So based on the last step, I have placed the values of ui and vj on the matrix. Now the next step is to calculate the net cost change for each water square. So in the previous step, using the stone squares or the squares where we had an allocation, we obtained the value of ui and vj. Now in this step, we'll calculate the net cost change for the water squares. That means the squares without any allocation. So in this matrix, let me note down the unit cost of the water squares with the red color. Now for the water squares, ui plus vj is called the implicit cost, whereas cij is called the actual cost of the cell. And the net cost change is calculated by finding out the difference between the two, which is cij minus ui plus vj. So let us find out the value of Cij minus Ui plus Vj for each of the water squares. So let me create a table for ease of calculation. Water squares, then Cij minus Ui plus Vj, and then net cost change. So the first water square is FAS4, Cij is 13, Ui is 4, Vj is minus 1. So 4 minus 1, which is 3, 13 minus 3 is 10. The next water square is FASD, Cij is 0, minus Ui is 4, plus Vj is minus 6. So 4 minus 6 is minus 2, and then there's a negative sign outside. So minus minus plus, so the value is 2. The next water square is FBS1, Cij is 13, Ui is 6, and Vj is 0. So 13 minus 6 is 7. The next water square is FBS2, Cij is 11, Ui is 6, and Vj is 2. 6 plus 2 is 8, 11 minus 8 is 3. The next water square is FBS4, Cij is 8, Ui is 6, and Vj is minus 1. 6 minus 1 is 5, 8 minus 5 is 3. The next water square is FCS1, Cij is 14, Ui is 2, and Vi is 0. So net cost change is 14 minus 2, which is 12. The next water square is FCS3, Cij is 10, Ui is 2, and Vj is 4. So 2 plus 4 is 6, 10 minus 6 is 4. The next water square is FCS4, Cij is 13, Ui is 2, and Vj is minus 1. So 2 minus 1 is 1, 13 minus 1 is 12. The next water square is FCSD, Cij is 0, Ui is 2, Vj is minus 6. So 2 minus 6 is minus 4, and there is a negative sign outside, so minus minus plus, so this becomes 4. Now the next water square is FDS1, Cij is 9, Ui is 9, and Vj is 0. So 9 minus 9 is 0. The next water square is FDS2, Cij is 11, Ui is 9, Vj is 2. So 9 plus 2, 11, 11 minus 11 is 0. And the last water square is FDSD. So FDSD, Cij is 0, Ui is 9, and Vj is minus 6. So 9 minus 6 is 3, and there's a negative sign outside, so this becomes minus 3. Now after we have found out the net cost change values, the next step is to evaluate the solution for optimality by reviewing the sign of the net cost change values. If all the values are positive, then it means that the optimal solution has been obtained. But if any of the values is negative, that means that there is further scope of improvement of the total cost. So here we have one square which has a negative net cost change. The square is FDSD. So this means that the optimal solution has not yet been reached. So now we'll have to iterate towards optimality. Now the first step in iterating towards optimality is to select the water square with the largest negative net cost change. Now in our case, we only have one square which has a negative value. So we'll choose this square FDSD and proceed with the next steps of arriving at an optimal solution. So this is the initial basic feasible solution that we want to improve, and this is the square which has the largest negative net cost change value. Now let us create a closed path starting from this square, passing through the squares using horizontal and vertical lines, and making a right angle turn only at the allocated cells. So the closed path will be FDSD to FDS3 to FBS3 to FBSD and then back to FDSD. Now let's place alternate plus minus signs, starting with the plus sign at the water square. So this is plus, this is minus, this is plus, and this is minus. And of course, why we are doing is because we want to make an allocation to this square FDSD because it had a negative net cost change, meaning that if we make allocation to this cell, then our overall transportation cost will reduce. And by putting the alternate positive and negative signs, we are ensuring that if we make allocation to FDSD, the remaining supply and demand constraints are not violated. Now we have to subtract the smallest of the figures from each square at the negative sign on the closed path and add to each square at the positive sign on the path. So there are two cells with negative sign. One has the allocation of 15 units, the other has 30 units. So the smallest value is 15. So we'll add 15 units to the squares with positive sign and subtract 15 from the squares with the negative sign. 15. Here 15 minus 15 allocation becomes 0. Here 55 plus 15 allocation becomes 70, and here 30 minus 15 allocation becomes 15. Now the next step is to prepare the new transportation table and check for optimality. So this is the changed solution after the first iteration. I have subtracted 15 from FBSD, so now the allocation is 0 here. Added 15 to FDSD, so allocation is 15. Subtracted 15 from FDS3, so remaining allocation is 15. And added 15 to FBS3, so the allocation now is 70. Now let's first find out the total cost for this solution. So the total cost is 25 multiplied by 4 plus 5 multiplied by 6 plus 20 multiplied by 8 plus 70 multiplied by 10 plus 30 multiplied by 4 plus 15 multiplied by 13 plus 20 multiplied by 8 plus 15 multiplied by 0. So this is equal to 25 multiplied by 4 is 100 plus 30 plus 160 plus 700 plus 120 plus 15 threes are 45, 4 carry over, 15 ones are 15 plus 419 plus 160 plus 0. So let's add the unit place, so which is 5. Let's move to the tens place, so 0 plus 3 3 plus 6 9 plus 0 9 plus 2 is 11 plus 9 is 20 plus 6 26. 2 carry over, 2 plus 1 3 plus 1 4 plus 7 11 plus 1 12 plus 1 13 plus 1 14, so 1465 rupees. Now just to remind, the basic initial feasible solution had a total cost of transportation of 1510 rupees. So the original one was 1510 rupees. So definitely we have improved the total cost of transportation. Now let's find out if this solution is optimal or not. Now before we proceed for the optimality test, we have to first test whether this solution is acceptable to proceed with optimality test or not. So the first condition for the acceptability test is that the number of allocations should be equal to m plus n minus 1. Now m is 4, n is 5, so 4 plus 5 is 9, minus 1 is 8. And let's count the number of allocations. So 1 2 3 4 5 6 7 and 8. So the number of allocations is equal to m plus n minus 1. So the first condition is met here. The second condition is that the allocation should be in independent positions. So if we check, all the allocations are in independent positions, so that condition is also met. So now we can proceed with the optimality test. Now the first step in the optimality test using modified distribution method is to set up a cost matrix containing the unit cost associated with the cells for which allocations have been made. So this matrix shows the unit cost of the squares which have allocations made to those squares, or in other words, these are the costs for the stone squares. Now the next step is to assign the variable ui and vi to each row and each column. So this is u1, u2, u3, u4, and v1, v2, v3, v4, v5. The next step is to compute the values of u and v for the stone squares such that ui plus vj is equal to cij. Cij is the value of unit cost mentioned in these squares. So for the first square, u1 plus v1 is 4. So u1 plus v1 is equal to 4. Second, u1 plus v2 is 6. So u1 plus v2 is 6. Then u1 plus v3 is 8. u1 plus v3 is equal to 8. u2 plus v3 is equal to 10. Then u3 plus v2 is equal to 4. The next is u4 plus v3 is equal to 13. The next one is u4 plus v4 is equal to 8. And the last one is u4 plus v5 is equal to 0. Now again, since we have taken here m plus n, that is 9 variables, however the number of allocations is m plus n minus 1, which is 8. So we'll assume one of the variables as 0. So let's assume v1 is equal to 0. So now let's find the values of u1, u2, u3, u4, v1, v2, v3, v4, v5. So v1 is 0, so u1 becomes 4 while v1 is 0. Now u1 is 4, so v2 becomes 6 minus 4, which is 2. So u1 is 4 and v2 is 2. Now again substituting u1 in this equation. So 4 plus v3 is equal to 8. So u1 is 4 from the previous equation, and v3 becomes 8 minus 4, which is 4. So v3 is equal to 4. Now v3 is 4, so u2 is 10 minus 4, which is 6. So u2 is equal to 6 and v3 is equal to 4. Now in the next equation, v2 is 2, so u3 is 4 minus 2, which is 2. So u3 is 2 and v2 is 2. And the next equation again, u4 plus 4 equals to 13. So u4 is 13 minus 4, which is 9. So u4 is equal to 9 and v3 is equal to 4. Now in the next equation, u4 is 9, so v4 is 8 minus 9, which is minus 1. So u4 is 9 and v4 is minus 1. For the last equation, u4 is 9, so v5 is 0 minus 9, which is minus 9. So u4 is 9 and v5 is minus 9. Now the next step is to calculate the net cost change for each water square. So for this step, I have noted the unit cost for all the squares. The ones in black are for the squares which have allocations, while the ones in red are the ones which do not have allocations, or the water squares. Now the net cost change is equal to Cij minus Ui plus Vj. So basically in the previous step, we had used the unit cost values of the stone squares to find out the values of Ui and Vj. And now we'll compare these values of Ui and Vj with the unit cost value of the water squares to find out the net cost change. So let me make a table here for easier calculations. Now after we have evaluated the net cost change values for all the water squares, next step is to evaluate the solution for optimality by reviewing the sign of the net cost change values. Now if all the signs are positive, then the optimal solution has been reached. So here we don't have any negative net cost change value, which means that the solution which we are testing for optimality is actually the optimal solution. And for that solution, our total transportation cost was equal to 1465 rupees. So this is the total transportation cost for this transportation problem.